Okay, so this is the start of section 5.2. We're going to talk about two things here, the addition rule and the complement rule. It's sometimes helpful to visualize a Venn diagram when working with probability. A Venn diagram is a picture that illustrates the relationship between one or more events in the sample space. And the rectangle represents the sample space, and each circle represents an event. Okay. Another definition, let S denote the sample space of a probability experiment, and let A denote an event. Then the complement of A, denoted by an A with a C in the upper right-hand corner, is the set of all outcomes in the sample space that are not in A. Okay, so problem 18, shade the region on the Venn diagram that represents the probability of A complement. So here's the probability of A. Anything that's in A is going to be in this circular region. Okay, here's the sample space. Anything that's outside of set A, I'd shade. Okay, and that shaded region would represent the probability of A complement. As a note, remember that the second rule of probability says that the sum of all the probabilities of all the outcomes must equal 1. Okay, in a Venn diagram, if we were to shade the entire rectangular region, the probability of sample space would be 1. Okay, so if I were to shade this entire rectangle, the probability of me being in the shaded region would be 1, or there'd be a 100% chance that I'd hit a shaded region if the whole thing was shaded. The complement rule says that if A represents an event and A complement represents the complement of A, then the probability of A complement is 1 minus the probability of A. Okay, and by the way, the 1 comes from the probability of the sample space. Okay, so you could define this as the probability of A complement equals the probability of the sample space, 1, minus the probability of A. So you're taking everything in the rectangular region and you're subtracting everything in A, and you're going to have what's left over, which is the A complement. Problem 19 is where we want to shade the region on the Venn diagram on the left that represents the probability of A and B. Okay, and then shade the region on the Venn diagram on the right that represents the probability of A or B. Okay, and so if I'm in A and B, I'm going to shade in the overlap. Okay, and by the way, this is just in general how we want to draw a Venn diagram with two events in the sample space. Okay, and we'll talk about the term mutually exclusive in just a moment. But so and means overlap. Okay, and this will be the probability of A and B. Now or, so if I'm in A or over here in B, I can be in A and B. So this shaded region represents the probability of A or B. Okay, where you're shading in both circles together. From that, we have the general addition rule. Okay, and the general addition rule says that for any two events, A and B, the probability of A or B, this guy here, is where I take the probability of A plus the probability of B minus the probability of A and B. Okay, by the way, why are we subtracting the probability of A and B? Well, it's because I don't want to count this overlap twice. And if I would have had the probability of A plus the probability of B, I would have done that. I would have counted this overlap twice. Now, in probability, you don't want to overcount anything. Okay, so I'm going to subtract one of the times where I've counted this region twice, this overlapping region. That way, I've only counted these three regions one time, and that's the general addition rule. Okay. Now, one of the things that we'll have to pay attention to when we're reading these problems is if we have mutually exclusive events or not. If events A and B have no outcomes in common or cannot occur simultaneously, then they are said to be mutually exclusive, or disjoint also means mutually exclusive. Your book will use the term mutually exclusive, okay? Although some books use the term disjoint. A Venn diagram of mutually exclusive events is shown below. Okay, so here's everything in A, and here's everything in B. Now, it's impossible for the two events to overlap. Okay, and that's what I mean by mutually exclusive. ME will represent mutually exclusive. Okay, if I have to write out the term, and I will, okay, a few times. Okay. Now from that, the addition rule for mutually exclusive events says that if two events A and B are mutually exclusive, then the probability of A or B is where I take the probability of A and then add the probability of B. Now you can still think of this as using the general rule, okay, but what is the probability of A and B? Well, A and B is the overlap, right? So what is the probability of being in the overlap? That's 0. There is no overlap. Okay, so I can think of this as the general addition rule, is just I'm subtracting 0. Okay, so one of the things that we're going to have to do when reading these problems, as I started to say, is we're going to have to know if we have mutually exclusive events or not. Now that's not something that they're going to tell you in the problem. Okay, that's something that you have to think about on your own and think is it possible for the two events to occur at the same time? Okay, because if it is, I need to use the general addition rule. If it is not, then I need to use the addition rule for mutually exclusive events. Let's take a look at problem 20 there, where it says, let the sample space for an experiment be the counting numbers 1 through 10, and let A, B, and C be events in the sample space. Part A, what is the probability of A complement? Okay, so I want to use the complement rule, which says the probability of A complement is equal to 1 minus the probability of A. The probability of A, there's 6 things in A out of the 10 things in the sample space, so 6 over 10 would be the probability of selecting something in A. So 1 minus 6 over 10 gives me 4 over 10, and 4 over 10 reduces to 2/5. Okay? And by the way, I think this would be a very easy question where you can just go right to the answer. Like, you don't need all this stuff. Okay? So what's the probability of selecting something that's not in A? If there's 10 things in the sample space and there's 6 things in A, then that means that there's 4 things not in A. 4 over 10. Reduce that. Okay? What's the probability of A or B? Okay, so I need to use the general addition rule, which says take the probability of A plus the probability of B minus the probability of A and B. The probability of A, we've already found, that's 6 over 10. The probability of B, there's 5 things in B out of the 10 things in the sample space. And the probability of A and B. Okay, and means overlap. And by the way, that's what I want you to think of. Whenever you see the word and, I want you to think overlap. Okay, so what is everything in A and B? Well, let's see. 2 is in A and it's also in B. 4 is in A and it's also in B. And 8 is in A and it's also in B. 3 over 10 then would be the probability of selecting something that is in both A and B. And that's what I'm subtracting. I've already got my common denominator, so I can just add the numerators. 8 divided by 10 would be the probability, and that reduces to 4/5. Okay? Part C, are A and B mutually exclusive? No, because mutually exclusive means that the events cannot happen at the same time. Okay, and here there's 3 things. We've already said that they're the elements 2, 4, and 8. That can be seen in A and B. Okay, so no, they would not be mutually exclusive, since the probability of A and B is 3 over 10. Part D, what is the probability of A or C? Okay, well, again, I want to use the addition rule. So the probability of A is 6 over 10. The probability of C, there's 3 things in C, out of the 10 things in the sample space. So 3 over 10 would be the probability of C, minus the probability of A and C. Okay, so how many things are in A and at the same time in C? None of them. Okay, so I would be subtracting 0. Add the numerators there. 9 divided by 10 would be the probability of A or C. are A or C, are A and C mutually exclusive? Well, yeah, they are, because there's no events in A and C. Okay, so they would be disjoint. Okay, you could say something like, yes, since the probability of A and C is 0. So, in any way that you think of it, I'm still using the general addition rule. Okay, it's just I need to know what that number is that I'm subtracting. Is it 0, or is it some other number that I got to compute? Again, that obviously makes a difference in getting the right or wrong answer. So here would be 0. Problem 21 says, let E and F be two events with the probability of E equal to 0.25, probability of F equal to 0.45, probability of E or F equal to 0.52. What is the probability of E and F? Okay, so here I need to use the general addition rule, and I've started by writing that down for the events E and F. And then I'm just going to fill in the information that I know. Okay, I know 3 out of these 4 items. So the probability of E or F is 0.52. The probability of E is 0.25. The probability of F is 0.45. I need to find the probability of E and F. Okay, well, 0.25 plus 0.45 would be 0.7. 0.7 minus the probability of E and F. If I subtract 0.7 from both sides, 0.52 minus 0.7 is negative 0.18. That would be equal to negative the probability of E and F. Multiply both sides by negative 1 to get rid of those negatives there. And the probability of E and F would be 0.18. Okay, so that's an example where I'm using the general addition rule. There's a couple of those in the book, by the way. Okay, problem 22 says a golf ball is selected at random from a bag. The bag contains 9 Titleists, 8 max flies, and 3 top flights. Part A, what is the probability that the golf ball is a max flight or a top flight? Okay, or is a key word, so a probability of max flight or top flight, or means add. Okay, so I take the probability of getting a max flight plus the probability of top flight. And then, now, do I have mutually exclusive events or not? Yes, I do. Okay, since it is not possible for the ball to be a max flight and at the same time a top flight. That can't happen. Okay, so in this formula here, I'd be subtracting 0. Now, they didn't tell me that I've got mutually exclusive events going on. That's something like, as I mentioned earlier, that I have to think on my own and see if I have mutually exclusive events or not. The probability of getting a max fly was 20 golf balls total in the bag. If I take 9 plus 8 plus 3, 8 of those are max flies, 3 of those are top flights. So 11 over 20 would be the probability of getting a max fly or a top flight. Part B, what is the probability that the golf ball is not a top flight? Okay, so the probability of top flight, but the complement of that, if I want the ball not to be a top flight, that's what I'd write. And I'm going to use the complement rule, which says take 1 minus the probability of getting a top flight. The probability of getting a top flight, I've already said earlier, this is 3 over 20. 1 minus 3 over 20 is 17 over 20. Okay. Now, in a problem like part B, I'm not sure we needed all this writing. We could have run right to the answer. Okay, so if I want the ball not to be a top flight, it means it's not going to be I get 20 balls in the bag total, subtract 3, 17 over 20, and I'm done. That means it's going to be a Titleist or a max fly. And by the way, I would also say, for now, like I'm writing out everything, okay, and I would encourage you guys to do the same thing, just because of chapter 5 is very wordy with what they have to say, and I highly recommend you write out everything, okay. If you don't, that's fine, but you don't want one little word to trip you up, okay. And So we'll definitely see that. Okay. Why don't we stop right here in the notes, and I'll pick up with problem 23 then when I get back.